Hello, now we're going to do some demonstration with time. Time is one of the most important quantities in the international system of units. And the unit for time in this system is the second. And time is today so important that most part of the technology we have depends on the capability to measure well time. And not only that, but time is so important that being able to measure well and define well second, we are also able to define other quantities, other units related to electricity, related to current, right? Electrical current and many others that we use in the daily basis. At the present way of living, time is so fundamental that we could not give up. Navigation system, everybody uses the GPS today. Telecommunication, can you imagine if we don't measure well time, how can a billion persons talk with another billion persons by cellular phone if there is no synchronism between this all information? Computer, everything needs time. We live today based on time. So it is very important that science has evolved enough to not only define well, but to realize well, to measure well time. Okay, so how we measure time? We can define the second, but we need to measure. And to measure time, we need a clock. And a clock is a device that has some periodic event happens, like the rotation of the Earth. Right? We know that Earth varies a little bit its rotation, but that's not important. If I don't want a very high precision, I can define the time based on the rotation of the Earth, because this is a periodical event. Happens each 24 hours again and again. Or even the translational motion of the Earth around the Sun. This is also very important periodic motion that we can use as time. Normally, a clock is a periodical motion together with a counter, something that can count those events. If I can count well, I can measure well. If I have a good periodic event happens and I have a good counter, I have a good clock. And this is what we're going to do in those demonstrations, is how our way of measuring time and defining the second evolved during the time until the present moment, where we rely on the atomic time and in some fundamental quantity in the atom. There are many ways of measuring time and define. We start by measuring the time. The pendulum of Galileo and everything, as we're going to demonstrate, were very good ways of measuring time. And but we had to define the second, and we defined second. One of the definitions historically important is we define the second as the time that the Earth goes around the Sun. If we can measure well the time that the Earth goes around the Sun, that's 1 year, and divide that by a huge number, as you can see on the screen, if we divide that, we can define the second. And for a long time, we define the time based in what we call the ephemeris time, which is a fraction of the year of the translational motion of the Earth around the Sun of the year 1900. And this is a definition we define. It's hard to realize because the year 1900 is passed, and we have to go back there and be able to trace back how long was the duration of the translation, the year at that year, and then define the second. But then things evolve, and we were able to create mechanical devices that can measure more precise and in a better definition the time and the second itself. As we just said, to realize the second, doesn't matter how I define, I needed to measure. And the pendulum was a nice way of measuring time. It comes back to Galileo's time, and as we know, the motion of a pendulum, everybody knows what's a pendulum, right? The motion of a pendulum is some periodic motion that can be used to measure time. And the pendulum is actually not so bad. We had clocks, the grandfather clock still has a pendulum in there, everything. And pendulum is good because, it has a precise period of oscillation, right? And this period of oscillation, let's go and measure this period of oscillation. I have a big chronometer here, and I'm going to measure how long it takes for a whole period of the pendulum. It means it starts here, goes here, comes back here. This is called the period of the pendulum, right? And the inverse of that is the frequency of the pendulum. So time and frequency is always connected, and we have to know that. Okay, so I'm going to release the clock and measure how long it will take because it's hard to measure one, I'm going to measure a few. So I'm going to start the clock and release the pendulum at the same time. And measure 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 oscillations was about 15 seconds, so this pendulum oscillates about 1.5 period. It gives 10 oscillations in 50 seconds. So, I mean, I could, and if I go further, if I increase the amplitude, this doesn't change. Doesn't matter if the pendulum oscillates very small or a little bigger. That is a small deviation, but that's not the case. So, I mean, we can use the pendulum, and it was used for a long time. But the problem is, define the second that way. Oh, and there is a good thing about the pendulum. Doesn't matter the mass. If I change the mass, you see, this is a big ball, this is a small ball. If I change now, if I put a small ball in here with the same length, they have the same length as you can see. If I put a small ball and I come and I measure what is the period of oscillation of this, because if you're going to construct a pendulum, I may construct with a tiny little ball, you may construct with a bigger one. So there will be a confusion. So let's measure this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Well, a small deviation because I am imprecise, but it's about the same, right? It's about the same period. And a nice way to see that's about the same period of oscillation is by putting them together here, because they have the same, and release them at the same amplitude at the same time, and you're going to see that they oscillate together, which means they have the same period of oscillation. Okay, so this is good because the pendulum, doesn't matter the mass I put in here, it oscillates with the same period basically. Now, but pendulum has an inconvenience. If I take the same mass, so I could define, but if I put a different length, now I'm going to make a measurement with a short length. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so you see that 10 oscillations was 1.2, before was 1.5. So shortening the length of the pendulum, make the period smaller. So even though doesn't matter the mass that we put, so then it's good because there will be no big variation if I take it, if I add mass or if I subtract mass, but it's very dependent on the length. And the length varies a lot. So even though the pendulum is a good way of measuring, it's not good because it's not reliable. It varies a lot. Will not be precise, will not allow us to have good reproduction. So pendulum is a nice clock, but it's not precise. One way of fixing the problem is comparing the pendulum, which is an oscillator, right, with something else that maybe is more precise. And this gives us opportunity to try what we call, let's introduce a feedback system to make the pendulum a good thing. So for us, the pendulum will be the oscillator, right? So here I have another system. I have now two oscillators that are coupled. I have a spring and mass, and I have a pendulum. And what is interesting is when I put the pendulum to oscillate, it somehow couples to the spring, and the spring starts to oscillate as well. The spring has a precise frequency of oscillation. And once I have a fixed mass and a fixed spring, it oscillates in the right frequency. Right. And then I have the pendulum. The pendulum, I produce a pendulum, and then what's good on the pendulum is that I can vary the frequency, but also when I have this oscillator not excited, not with energy, and I put this to oscillate, there is a coupling of the energy of this pendulum with this one, with this oscillator. Depending on the frequency, so if I have a fast frequency, so if I have a small, this is a long pendulum, so I have a frequency like this. So if I have a frequency like this, so if I go to a very long pendulum, you know, and I see also does not make the mass spring oscillates a lot. So, you know, does not couple the energy of this oscillator to that one. But if I go to a very precise length, right, if I go to a precise length and put the pendulum to oscillate, I couple a lot of energy to the pendulum, to the mass, to the spring mass. So somehow I can vary the frequency of the pendulum by varying its length and check with this one, because this one has a precise frequency of oscillation. So I can somehow control, if I have a reference, I can control the length of the pendulum until I reach the precise frequency where I couple more energy to this oscillator. And this is what I call resonance. So I'm going to start with this pendulum. It's short, and I'm going to put it to oscillate, and I'm going to observe here the spring oscillating with the mass. Okay, so this is, it's not coupling a lot, and I'm approaching to a point where it seems to be start to move. Now see, observe this, how many energies coupling, and if I keep passing, if I go to very long range now, very long pendulum, this is stop oscillate a lot. So I can control. If I want to have a precise length of the pendulum, I can come here and say, look, I'm going to use the pendulum and I'm going to make it oscillates. And I know that always that it is making the mass oscillating a lot means that I am in the right, around the precise length. This is called a feedback system. And normally, to measure time, we use these two oscillators. We use something that oscillates and we can control and measure because we know precise the period of oscillation of the pendulum, and we use this as a reference. And always that we make a pendulum that oscillates with this reference, we know that the pendulum has precise the right period of oscillation. So we have a way of comparing a reference with a pendulum. Here we use a spring, and the mechanism is, I mean, you already find out, right? As this oscillates, it makes this ruler to go up and down with the same frequency. And when this is, if I go this very fast, I don't excite the spring. But if I go in the right way, I make the spring goes very fast. So fast that it blows up. Now imagine that I have somehow a very good reference here that I can choose. And then I can use this oscillator to always couple, to always make this to oscillate in a precise way and use this frequency that's compared to that one as the reference frequency. And then I have a good measurement of time and a good definition of the second. Besides the improvement of the oscillators that we use as clocks, which help us to really measure and to implement the second, quartz oscillators were wonderful, and they help us a lot to improve technology, to improve the way of measure. You can see those wrist clocks, washers, right, that are wonderful. They have very high precisions, but that were not enough. We need to improve even more. We need to get better measurements of the second. And that came the idea to use the atoms, because you see, if we measure frequency, we somehow have time, because the inverse of frequency is time. And the physicist improves a lot in understanding how we can interact with atoms. And atoms are equal You know, if I take an atom here and in the moon, they're basically the same. And they have a specific frequency of excitation. They are like pendulums or spring and mass with very high precision. And then this whole thing evolved to the idea to have the atomic clock. The oscillator that we're going to use as a reference now, instead of the spring and the mass, is now an atom. An atom has electrons, and when we excite those electrons, when we make the electrons to absorb energy, it only happens in some specific frequencies. I have to give the electrical and magnetic field in some specific frequency to promote electrons to other excite. And each atom has specific frequencies to be excited to promote the electrons from one energy to the other. And then the idea to use atoms as this reference oscillator came about and became the standard, became the way of measuring time and the way to produce the most precise second that we can do. Now, to understand this, we have to understand the way we talk with atoms. And the way we talk with atoms is through electromagnetic waves. Well, the name is already saying it's waves are things that oscillate in time and in space, right? And light is an electromagnetic wave, is the one that we see all the time, and depending on the frequency we don't see, but it's there. And to explain to you how is the electromagnetic wave, we're going to do a demonstration of waves. It's very hard to see the electromagnetic wave oscillation itself. We normally observe the light, but it's very hard to see that there is some electrical field or voltage oscillating there and a magnetic field oscillating there. And this is the way that we talk with atoms, because atoms are charged. And when we put this electrical field or magnetic field oscillating, it likes to interact with charge and makes the charge to oscillate. And because they can only oscillate in a very specific way, I can only excite when I produce the right frequency of electromagnetic wave to excite the atom. And that's the way we talk with the atom, and we can use the atom as a precise oscillator. So let's do a demonstration here. And because I told you it's hard to see electromagnetic wave oscillations, we're going to do water waves instead. And water waves, if you are smart enough, we can simulate everything that happens when electromagnetic wave interacts with atoms. Okay, first of all, I have to show you what is a wave. Here I have a water tank, and the water is the medium in which we're going to produce oscillations. The oscillations here is like the waves in the sea. It's water going up and down, but the water actually does not propagate. What propagates is the energy that I'm putting in the water. We're going to introduce waves, shine waves on the atoms here, and you know, we're gonna do, and as you can see, you see the detail of the camera. We are looking how much energy we couple, how much we can excite this cloud, which represent my atoms, which is represented here by this black ball. If I go to very high frequency, if I even increase the frequency, as you can see, almost nothing happens to the mass. I cannot really transfer energy to that. But if I start to change the frequency, well, you may think that if I put more frequency, I may be able to excite this, to make this to shake, but I cannot. Now, if I go down, I will reach a frequency, a specific frequency, where you see that started to excite. And this is how we excite the electrons in the atoms. We go to that right frequency where the energy couples to the electrons and start to shake the electrons. If I go too low, I pass, I miss it. I am not exciting anymore. If I go too high, if I start to raise up the frequency, I reach exactly the frequency where I'm exciting this cloud and I'm producing the excitation in the precise frequency that I excited this. And if I go even higher, I stop to excite. You know, you think it will be better, but it's not. So the atom excitation responds to a very specific frequency. And then you can see that it's shaking up and down, is really exciting, and that frequency is the natural frequency of the electrons absorption of these waves. And as you can see, when I excite, the cloud now is giving to the medium waves back, spread random, spread in all directions. This is the emission of the atoms that sometimes is what makes us to see the things, is the light that is emitted by this cloud and comes to us. And by looking at that, I know that the atom is in exactly the frequency, because you see, now I'm exciting the atoms and it's giving energy back. And then if I have control of this frequency, I can excite the atom and see this. And if I start to go much slower, oh, it's not exciting and it's not giving anything back. If I go even further, if I go with higher frequency, I pass to the excitation, but then I stop excitation. Waves are passing through the atoms if the atom does not exist there. This is what's happening in the real world. I'm exciting the atoms, and then by looking what's giving me back, I know the frequency, I know precise if that frequency is exciting the atom. And that's the way we use the atoms as a reference. Because now, if I have a good control of this frequency, I go and I say, well, to precisely excite one atom, I need a specific frequency. If I can vary this oscillator, producing waves and shining this wave through the atoms, I reach the frequency where I excite. And then I say, well, now I am in the precise frequency. And because all atoms of one type has the same frequency of excitation, I can use this frequency. And I can see, even if I'm not looking to the atom, I can see these waves coming, because atoms are absorbing and gives us back in a process that we call spontaneous emission. And that's the way we can use a generator of electromagnetic wave and an atom together to make a clock. Because here in this knob now, I can know precisely the frequency. And if I know precisely the frequency, the inverse is the time. And that's the way we can define the time, is by using the atom as my reference and producing an oscillator that's electromagnetic waves that will precisely excite the atom. This is an atomic clock. In order for you to believe what we just said, we're going to do an experiment that shows to you the light coming from atoms and molecules in an experiment. Here I have an ampoule that has iodine inside, and I have here a laser, as you can see in my hand. So a laser is passing through this cell, and the cell has a vapor. And of course, this is the real electromagnetic waves, the waves that comes from a laser. And they are interacting with the iodine molecules in here. And I'm going to change the frequency, the same experiment that I did with the water tank, but now with the real molecules. So you can see and observe the flashing, the light coming from the molecules that we use to determine the frequency that is in the laser. Okay, so let's observe. We're going now to make the room dark so we can see the fluorescence, and a camera will pick up the image here. So let's start to move the frequency. You see there is a laser here, and the laser is passing through the cell. This is an iodine cell, and we're going to start to see what's coming out of this cell containing molecular vapor of iodine. So let's turn off the light, and we're going to observe here the light coming. As I scan the laser, you see this beam of light coming from the cell. That is the fluorescence of the molecules there. This is exactly the point where we pass to the resonant frequency of the molecules that are there. And if I know this frequency, this always will be the same frequency. This is exactly what we do when we investigate the atoms to define the second. So the cell and this light coming out when I move the frequency up and down, and I reach exactly the precise frequency that let me see the molecules by seeing the light that they emit. This is actually the atomic resonance seen there, and only happens in a very specific frequency. And if I know this frequency, I know exactly what it is. If I can define, always I have this molecule and I have a laser, I can precisely determine the frequency by looking to this resonance.